Welcome back to STEM Online Academy. Today we're going to be looking at specifically a Fourier series. And what we're going to do with that Fourier series is we're going to use it to derive a very interesting result. This guy right here. Okay. All right. So this guy down here that I'm going to highlight, right? This sum here, y it's equal to 1 is equal to pi squared over 6. Okay. Now, most students will just memorize this result. Okay. But if you ever wondered why pi shows up in a sum over integers, this video is for you, okay? And specifically, you'll notice that this summation is actually in the form of a Riemann zeta function, okay? Where our n to the exponent is exponent 2, all right? But there's multiple ways to derive it, but I'm going to derive it using Fourier series, okay? Today, I'll show you how this result comes directly from Fourier series, okay, using only undergraduate calculus, okay, and some, plain visual reasoning. It's just mainly undergraduate calculus, okay. No tricks, no memorization, nothing overly fancy, okay. All right, so I'm going to circle this result here, all right, this pi squared over 6, okay. So let's get right to it. So our goal is simple. We want to evaluate the infinite series. Okay, we want to evaluate the sum, right? So right over here. So we want to evaluate the sum from n equals 1 to infinity of 1 over n squared. Okay. All right, and this is sometimes called the Bessel series or Bessel problem. Okay. And you often see the answer quoted, but very rarely derived in a way that actually explains what's going on in the series. Okay. So let that sit with you, right? Usually they don't talk about how this series derives the following result, but I'm going to go into the not all the details, but mainly most of the details how we get to that pi squared over 6. Okay. So let's start looking at that. Okay. Now, why is this important? And why am I bringing this up? The struggle what blocks most students. Okay. All right. Here's where most students get stuck. Okay. First, why does pi appear at all in this? Right? Why does pi even appear on the right-hand side of this series? Okay. We're summing over the integers. There are no circles anywhere. So where's the pi coming from? That's a question, and it's a good question, right? Where's the pi coming from? So that's the first thing. Second, what does this have to do with calculus? Okay. Second question we have to think about. What does this have to do with calculus? Third question, is this just something I'm supposed to remember? Right? These are all good questions. They're all very good questions, all three of these questions. And the answer is pi appears because this problem is secretly about waves. Okay? Yes, that's right. This problem makes sense when you put it into a geometric concept. Okay, I'm going to highlight waves. Just one sec. Waves. Okay, waves in capitals. Waves with red. That's right. Some type of wave. Okay? That's what we're going to be looking at. Yep. So to see this, we're going to look at a very simple function. Okay. All right. So we're gonna do that. All right. So let's look at that function that we want to evaluate. Okay. So we want to consider the function. All right. So let's consider some function. So this is going to be, I'm going to say proof here because we're doing the problem right now. Okay. So proof. Consider a function f of x. Okay. A basic function f of x is equal to x from negative pi to pi, not including the interval. Okay. Now, automatically, you'll notice that this function is odd. Okay. automatically, because if you tested f of negative x, input every x with a negative, it's to spit out a negative f of x, negative of the function. So since the function is x, it's going to be negative x. Okay, so f of negative x would equal to negative x, right? And that makes sense. Okay, so this function is odd. Okay, this function, I'm going to write here. Okay, this function is odd. Okay, odd. It's an odd function. Okay, highlight that there. It's an odd function. So what does that mean in terms of Fourier series? It means that we only need to look at the sine terms of the Fourier series. Okay, so we're going to use a Fourier sine series. Okay, that's what we're going to be doing. All right, so let's go to the next page. All right, and to give us a geometric construct of this. All right, if you look at drawing a graph, okay, I'm drawing a graph here. Drawing a graph here, okay. If you look at f of x, and it's defined from minus pi to pi, for instance, let's say from minus pi to pi on the interval here, okay, and f of x is x, so f of x is x, all right, you'll notice that our line will go all the way like this, okay. Now, remember, we're on minus pi to pi, our interval, okay. So what does that mean? Are the endpoints here included or not included? In other words, what I'm asking is there discontinuity or continuity at the endpoints? They should be open holes, okay? So I'm going to do it as open holes like this, because it's not included on the interval. I want to make this a bit more accurate. I want to spread all the way to pi. Okay, so on this side here, it's not included. Not included. You see what I mean? Because we're going from minus pi to pi. Okay, so that's not included on the interval. It's good to draw the basic function that we're dealing with here. Okay, we need to assume that f of x equals x is how we're going to prove this result. Now, you may be asking why. Okay, and probably thinking like, how am I supposed to figure out where the hell that even comes from? And this is quite often one of the most difficult things in mathematics. Is yes, a lot of things are deduced by reason, but quite often we need to use a sixth sense first. Okay, right? We sort of have to be able to intuitively feel what parameter, what function, what constraint we need to use on the equations. Okay, that just comes from a lot of problem solving. Right? You almost build an intuition of how to do it. At first, it's going to be very hard to do it, right? But it comes with a lot of practice. Okay. But yes, you will get the tools of how to build that sixth sense, right? And all it is just strengthening your problem solving, your visual spatial skills when doing hard problems, and then that's what's going to happen. It's going to be you're going to have almost like a very strong intuition of what function you need to bring in, what needs to be created, and so forth to solve a hard problem. Okay, all right, that'll make sense as we go along. All right, so let's continue. Now, we want to build the Fourier series, okay? So you want to building, building a Fourier series, or the Fourier series, okay? That's what we're going to be doing. All right, I'm going to build the Fourier series. Okay. I like this series a lot. It's probably my favorite series. All right. Yeah, I think it's it's one of my favorite series actually for some reason. This has to do with waves and harmonics. I like waves and harmonics. Okay, so just a reminder, since we're using a Fourier sine, f of x is going to be equivalent to the sum, right? So the sum from n equals 1 to infinity, okay, of my coefficient b sub n times sine as a function of n times x. This is defined as the Fourier sine series, okay? So this is the Fourier sine series. So definition, good to explain what you're doing on every step. Definition by the Fourier sine series. Fourier sine series. Okay. Now, what we need to do is figure out what our b sub n is, right? Because that's what we know what our f of x is. The b sub n is the coefficient that we need to look for. Because we have that, and we have our sum, we know what our function of x is. We need our function of x. We need to know what our function of x actually is. Okay. Right. To back step and put into our that Riemann zeta function here. Right. We're going to equate it somehow. All right. But let me get to it. So our b sub n, and you can verify this. This will be your homework. Okay. Let's try to verify. B sub n is done by doing this calculation. We're going to say that b sub n, the coefficient, right, is equal to 1 all over pi times the integral from minus pi to pi of f of x times sine of nx dx. Okay? Right? So if you have seen Fourier series and Fourier coefficients, this is a Fourier coefficient. There's a0, there's a sub n, b sub n. We're finding b sub n only because that's what we need to input into our Fourier sine series. Okay, so I hope this is making sense. Now, I have the b sub n. Okay. What you would do is you do this. I'm not going to go through the entire calculation, but it could be good practice if you want to try this on your own, right? The 1 over pi. We're integrating from minus pi to pi. Limits of integration have to be from minus pi to pi. Okay? Right? For obvious reasons, right? Can't be outside of this interval when using a Fourier coefficient. Okay, so minus pi to pi, and f of x was defined as x, right? So x sine nx dx. Okay. And what you should get, you can verify this for your homework, is that b sub n, I've already done this. I already know what the calculation gives me. I did it on the side, 2 times negative 1 to the n plus 1 power divided by n. Okay. This is the solution to the Fourier coefficient. Okay. But please verify the result for homework. All right. And if you have any difficulties understanding what on earth, how we get to that, you can always contact me for, through an email or for extra one-on-one explanations of exactly the reasoning, detailed reasoning of how I've gotten to the b sub n coefficient equal to that. Okay, so we got the b sub n. Now the exact derivation of these coefficients is not going to be the focus. That's why I just jumped to this. Okay, but you can verify for homework. And you can compare your results with mine if you want. You can, as I say, contact me or whatever. What matters here is not the derivation, the exact derivation of the coefficients. What matters here is the size. Notice the scaling factor of 1 over n, right? There's a scaling factor here of what I'm going to highlight, 1 over n. Okay, right? I'm going to underline that 1 over n, right? Well, I circled it. I think that makes over sense, right? That 1 over n factor there. Okay. Now, the critical step for this, okay, there's a reason why we calculate that b sub n. We need the b sub n to substitute into our Fourier coefficient to figure out what our f of x is, what our summation is. And the reason why we need the b sub n is because automatically we need to use something called Parseval's identity. Okay, this is the next step that changes everything. Parseval's identity tells us that the total energy of a function equals the sum of the squares of its Fourier coefficients. Okay, again, Parseval's identity tells us that the total energy of a function, yes, functions have their own energy, just like physical constants, right? In nature, have their own total energy, and it equals the sum of the squares of the Fourier coefficient. Okay, so we're going to use Parseval. Okay, something called Parseval's identity. So we're going to do that. And Parseval's identity states that if you take the summation, okay, summation from n equals 1 to infinity, okay, of your b sub n, the absolute value of b sub n squared. Now you see why I want to calculate the b sub n, right? Because logically, if I don't have my b sub n, I will not be able to use my Parseval identity. If I don't have my Parseval identity, I won't be able to equate this guy here to my Riemann zeta, my Riemann zeta function, the sum of 1 over n squared, right? The key here, why I'm using Parseval's identity is because the b sub n squared. There's a correlation between that and that 1 over n squared. Okay, that's why I use Parseval's identity. Okay, and then this is equal to 1 all over pi. I'm going to integrate from, I'm going to integrate from minus pi to pi of f of x all squared dx. This is known as Parseval's identity. Okay, this is the definition. Definition. Parseval's identity. Okay, it's Parseval's identity. Now for the computation, right? Let me show you how we calculate this very easily. Okay, with Parseval's identity on the left-hand side, you'll notice that if I take my 1 over pi and I integrate from limits of integration from minus pi to pi of x squared, it's x squared because f of x was x. F of x squared would be x squared. Okay, dx, you'll notice, by the way, this can be written more simply. It's a faster way than just doing an integral from minus a to a. I could have said that it's 2 over pi, and then I can integrate from 0 to pi. It makes the integration for the limits of integration easier to calculate afterwards, of x squared dx. Okay, and then from here, you'll notice something, that this now becomes what? What does this become once I integrate? Get out your integral methods here, people. Simple, very simple. It's just 2/3, right? Because remember, x to the n plus 1 over n plus 1 is when we integrate a power function, so it becomes 2x cubed all over 3 pi. Okay, but remember, I have to take my balance from 0 to pi. Okay, I hope that makes sense. And if you simplify this, okay, you will get, at the end of this, 2 pi squared all over 3. Okay. All right, so since I got 2 pi squared all over 3, that's the right-hand part here of Parseval's identity. Okay. All right. But since we know, let's go to the next page. Since I automatically know that, right? Since I automatically know that b sub n, okay, so b sub n is equal to 2 times -1 to the n plus 1 all over n, right? Therefore, remember, I want my b sub n squared. Why am I looking for b sub n squared? Why am I looking for my, and its absolute value, by the way? Why would I look for b sub n squared? Because that's what Parseval's identity requires. We need to know what our b sub n is before we can calculate our b sub n squared. This guy here, okay? So the b sub n, okay, is going to be equivalent, as I said above, we just square all that, okay? And we just going to get 4, let me just show you what I mean, right? So we're just taking this one, 2 of 2 times -1 all over n all squared. And then this now becomes 4 -1 squared over squared. That just gives me 4 all over n squared, okay? Over n squared. And you'll notice that's my b sub n. Yeah, that's my b sub n. B sub n squared, sorry. Okay, over n squared. So my sum from n equals 1 to infinity, right? So let me explain, right? Let me explain this. That since we now know, okay, right? So since, or I'll say because we know that, right? We know that the summation, right? So this right over here. Okay, so we know that our summation, okay, just make sure you're following along. I know this is a slightly difficult problem, right? So pause and retrace your steps on this. Remember, it's pre-recorded, so you can go through it again, ask yourselves questions, or you can always email me for questions how to do this. At sum from n equals 1 to infinity, okay, of 4 over n squared. Okay, that's from Parseval's identity, because you know what sum from n equals 1 to infinity of b sub n squared is, right? Will be the sum from n equals 1 to infinity of 4 over n squared. We know what our b sub n squared is. And this is equal to 2 pi squared over 3. Obviously, right? This is the left-hand side. Okay, this is the left-hand side of Parseval, right? Sum n equals 1 to infinity b sub n all squared. And this is equivalent to the right-hand side, the 1 over pi, right, integrated from minus pi to pi of f of x squared and then dx. Parseval's identity, okay? I'm just equating both sides, all right? Now, let that sink in. I'm going to erase this. All right, so now that we know that, notice that I can pull the 4 out because it's a constant. Okay. Okay, so pull the 4 out. And this is equal to 2 pi squared all over 3. Now, you're going to notice something here, right? What were we looking for? What were we planning to solve in this? What was the initial question? Let's look back here on the first page. We wanted to show that the infinite series from n equals 1 to infinity of 1 over n squared is equal to pi squared over 6. Okay, pi squared over 6. Notice this portion here. We want to rearrange for this and see if we get, because we want to rearrange for our infinite series of 1 over n squared. So I wanted to divide both sides, right? So I'm going to do that. Right? I'm going to take 4, right, times the summation. I'm going to divide both sides by 4. Just 1 second. Sum from n equals 1 to infinity of 1 all over n squared. Okay, parentheses, this is equal to 2 pi squared over 3. Okay, I'm going to divide both sides by 4, okay, to isolate for this infinite series. All right. Okay, so sum from n equals 1 to infinity of 1 all over n squared is equal to 2 pi squared all over 3 by 4, right? I'm dividing, isolating for the infinite series from n equals 1 to infinity of 1 all over n squared. And you're going to notice we get 2 pi squared over 12. 2 over 12 as a fraction is 1 over 6. Okay, so 1 over n squared is equal to pi squared over 6. And we have verified it. We have verified that the Riemann zeta function to the second power is equal to pi squared over 6. Okay, just by using Fourier series. Probably haven't seen that before. Good. Right, so we get our pi squared over 6. Pretty cool, huh? That's to be like a wow moment, right? Probably never seen that before. Or you have, but you've done it using a different method. Okay. Okay, so let's look at the interpretation of why this matters. Okay. So why does pi appear here? Okay, so why does pi appear? What's the interpretation? Because Fourier series lives on intervals because energy decomposes into frequencies. Okay, that's exactly why, right? Energy decomposes into frequencies. Okay, and because when you measure that energy, squares of coefficients appear naturally. This isn't a trick. This is just structure. Okay. All right. So this way of thinking, right? This way of thinking that I've showed you. Okay. This analysis, you could say, right? Looking for structure instead of memorization is exactly how both mathematicians and physicists solved hard problems, right? It shows up in signal processing, quantum mechanics, engineering, and advanced calculus exams. So a lot of applications, a lot of important things to consider, especially when it goes to standardized testing. Okay, let me show you actually something with signal processing here. Okay, so let's go to the let's go to desktop. You can see here, we're going to go to a simulation, really fast simulation. Okay, you can see that the decimal problem of the infinite series is equal to pi squared over 6. Here's an example of some form of signal processing. You can see here our sum, right? Partial sums of the summation climb upwards and settle towards pi squared over 6. So that's like a maximum limit that the summation can reach. Okay, this is pi squared over 6. All right, so again, let me show you. Okay. Pretty neat simulation. All right, so you can see here that we've got, and those dots there, right, those circular dots, normally press don't have it. This means it's a discrete distribution of some sort, right? It's not continuous, it's just discrete because it's a summation. It's not an interval. Okay, so you can see a discrete signal processing here, okay, with the partial sums. All right, so let's head back quickly. All right. So if you want to be able, right, if you want to train this kind of thinking, my book, Advanced Integration Techniques, right, develops these ideas systematically. And if you want help mastering things like calculus, series, ODEs, or physics, I also work one-on-one with students. Okay, so both links to where to find resources on my book, or the book itself, will be in the description below at the end of this pre-recording, and also coaching services if you need help with, as I say, calculus, ODEs, or physics. I'm always available. Links will be in the description. Okay, links will be in the description. Thanks for watching, and I want you to try that problem. And don't forget to like and subscribe, please. Right? So like and subscribe, support the channel. Okay? Have a great day, everyone.